But first, I think one thing that we could easily get out of this, let's see, we have two unknowns in the y, but right now we only have one unknown value in the x. That's this RAX. I think we could go in here and do a sum of forces in the x equation. And remember now, we're not in x prime, we're in x. X is going to the right. So I'm going to come down here and say, for the overall structure, I like to always, kind of give a label to what my equations of equilibrium are applying to, because if you had just done this free body diagram of the cart and then you just start drawing an equation that applies not to the cart but to the overall structure, it would be very confusing in your calculations. So just write like overall structure or entire structure, whatever you're going to write, and now we can develop an equation of equilibrium that works with that, because your equations of equilibrium always have to be tied to some free body diagram, whether it's the free body diagram of your overall structure or if it's a free body diagram of a component. So this one's for the overall structure. We can say sum of forces in the x equal to 0, and I can say going to the right is positive. That's going to give me minus RAX, because if you recall, RAX is pointing to the left. And then what else am I going to have? I am going to have the x component of RD and the x component of R sub E. Okay, and just maybe to help us out with this, because these angles can be tricky sometimes. If this is 60 degrees, that makes this 30 degrees. So our x components are going to be times the cosine of 30 for both of these vectors, R sub D and R sub E. So I've got minus RAX, and then I have R sub D, which is 0.167 kips, and that's going to be times, just like we said, the cosine of 30 degrees. And then I've got plus 2.333 kips, which is R sub E. And that's also times the cosine of 30 degrees. And that's going to equal 0. And that's going to tell me that RAX, when I solve for it, is equal to 2.165 kips. That's another one of our answers, 2.165. Let's go ahead and write that up on our free body here. That's 2.165 kips. And it was positive, which means our initial assumption that it was pointing to the left was valid. I think I'm going to isolate this free body right here, the free body of just the hoist, and that will make it a little bit simpler, because then all of this stuff down at the cart goes away and it gets replaced with the tension in the cable. So let's draw that free body, and again, I've got that one started for the interest of time. It looks like this, and I kept the part that I'm keeping. I got rid of the part that I'm getting rid of. I do need to label the values that I've gotten so far. I just have these letters here. I need to go ahead and turn them into numbers. So this was, what, 2.165 kips, and the tension was 4.333 kips, and the angle that that's acting at is 60 degrees. We know that from the inclination of all the structure at the beginning. The cable is running parallel to the ground. So if that's 60 degrees, that makes this 60 degrees as well. So there's our free body. I think it's got everything on it that we need, or at least everything on it that we know. And so we can do what? We can sum moments to get one of the vertical unknowns. That means we need to either sum moments at A or at B. It really doesn't matter which one. I'm going to pick sum of moments about A, because then RAX, it has fewer terms in it because RAX passes through A. So I'm going to do that. You could easily sum moments about B as well. Doesn't really matter that much. Again, I'll say counterclockwise positive. RAY and RAX, they, obviously they do not enter into this equation. I have RB, and it's acting at 2 feet is its perpendicular distance away from A. So I have RB times 2 feet, and that's going to be a counterclockwise moment, so it's going to be positive. And then I need to look at this tension in this cable. I don't know that angled distance from, the perpendicular distance from A to the cable. It's kind of funky. Again, I'm going to break it up into components and then just use the dimensions that I've been given here, these dimensions and these dimensions. So to do that, I need to break it up into components. I'm going to have the X component of the force in the cable there and the Y component of the force in the cable there. So the X component is going to just be the tension times the cosine of 60, because you can see my angle work right there. So this is going to be 4.333 kips times the cosine of 60 degrees, 2.167 kips. And then the vertical is going to be times the sine of 60. So this is 4.333 kips times the sine of 60 degrees, 3.752. Now that means that, let's do the X one first, I suppose. It doesn't really matter. We'll have 2.167 kips acting at a distance of 3 feet from point A. So we'll say times 3 feet, and that's going to be a clockwise moment, right? Because it's wanting to cause a clockwise moment about A. So we'll say that's negative. And then I've got the 3.752 kips, and that's going to be acting at a distance of 2 feet plus 4 feet, or 6 feet from A, and that's also causing a clockwise moment, so it will also be negative. Let's see, that's everything, so we can say equal to 0. So that gives me R sub B is equal to 14.5 kips. That is another one of our answers. I'll write it on this diagram too. So now we can do sum of forces in the y equal to 0. I'm going to say up is positive. RAX will not be in there, but RAY will. It'll be minus RAY plus 14.5 kips. And then just the y component of the tension in the cable, right? So minus 3.752 kips equal to 0. That will tell me when I solve for RAY that it will be equal to 10.75 kips. So that's everything. Those were also both positive, which means that my assumptions were correct. So we have solved for all of the reactions for this machine.